Yes, for the flow chart, you'll get a packet. You'll get the flow chart, the periodic table, and the character tables, just in case you need them. We haven't really done anything. Well, yeah, okay. Today we will talk about the transition dipole moment integral. That was in the homework. Let me show you one more time one of those examples. Okay, so let's just go through. Okay, there's that. I'm just fixing things on the computer. Okay, so let's quickly go through that. So this is applicable to the 1D box, 1D particle in a box. If we were to run this wave function through, we can't really run it through the flow chart because there's no atoms, right? So there's no linear or anything like that. But there is an inversion center on this. I was talking kind of about reflection of the wave function left and right, but actually that mathematically is an inversion center because we only have one dimension. And so if we're going from positive to negative x, we're inverting it, the wave. And so if we have this inversion operation, which now, our symmetry elements, the I operator, we can look at even and odd. So if we take the negative, this piece here at -2 here, and we invert this over, it's the same magnitude, same sign. So that's an even function. And so we can label psi1 as even. Here we go to the other side, and it's equal magnitude but opposite sign, so psi2 is odd. And then psi3 is even. We could do the same thing. And those characters here in our operation are in this character table. So this is what a character table is. It has the operations. We only have two symmetry elements, and we have the results of what happens to the wave function when we operate on the wave function with that operator. What happens to it? It comes back, but is there a character in front? Is it +1 or -1 or some other thing? And so if it's if under inversion it's +1, we give that designation an AG. This is the Millikan notation. We'll emphasize that word in a minute. But this now, the top row is the only even row, and all other rows are odd. And so we end up with AG for n equals 1, AU for n equals 2, and AG for n equals 3. And so on and so on. It keeps going up. It alternates AG, AU. G is German. You're going to learn some German in this course. G stands for gerade, which means even. Okay. So, and then U is ungerade, so uneven or not even. So even and odd is what we call those. So AG is even, AU is uneven. And you see those little subscript G's and U's only on character tables that have an inversion center. So they're not on everything. So let's see how we can use this. We've already done this problem, but we'll do it now with the AGs and AUs. We did O's and E's last time, like 2 lectures ago. So here's our character table, and then we have this thing called the direct product table. So this is a character table. And this is the direct product table. So this is all these Millikan notations, the symmetries present in that molecule multiplied by each other. Now they people are lazy, and scientists are people, so are mathematicians, and so it's a symmetric matrix, and so they're so lazy they just give you 1/2 the matrix. But this AU, it's symmetric, so this could also be AU. They just leave it out because they just save space and save toner, I guess. I don't know. It's strange, but so what we do is we can come up here and we can take our transition dipole moment integral and we can put in these Millikan notations. So you see these right here associated with n equals 1, 2, 3, 4, and 5. So we've assigned these symmetries to the individual wave functions and put them in here into the transition dipole moment integral. This seems almost too simple to bother with for one dimension, but when we get to a bigger molecule like benzene or water or whatever, this becomes more interesting. And you saw that in your homework with the A1 and the B1 and the A2 and B2. We were putting these together and forming these symmetries of those functions. And then we can combine them. We use the direct product table to combine them. So what is A AU times AG. So AU times AG gives the result AU. And so then we summarize those first two. You see where that came from now? It came from the direct product table. And then we summarize the next two, multiply them together. AU times AU gives AG. So this one now comes right there. And now we have the integral over all space of an even function. Top row in these character tables is even. All the other rows are odd. So if we have a top row here that's not equal to 0, and we say it's allowed by symmetry. So we got the same answer as we got with the E's and O's 2 lectures ago. But this is the more mathematical way, the correct way to do it, showing the Millikan notations from the character table. We can do the same thing over here with the 1 to 3 transition. AU times AG is AU, and then AG times AU is AU, and that is an odd function. It's not the top row of the character table. And so that is equal to 0, and this is forbidden by symmetry. So notice something. We can't get the direct product table, which tells us about our integrals, without the character table here, because that's where these pieces are. We can't get the character table without the point group. And we can't get the point group without a knowledge of the symmetry of the molecule, which requires a really good Lewis dot structure. So you see how much everything depends upon your ability to draw the molecule. If you can't draw the molecule well, you can't see the symmetry. You can't see the symmetry, you can't use the flow chart. You can't use the flow chart, you will get the wrong character table. If you have the wrong character table, you get the wrong direct product table. If you get that wrong, then you don't know about your selection rules. Okay. But once you get good at that, you can draw well and you can see the symmetry, then it's easy. Character table, direct product table, I know my integrals, I know if it's allowed or not. So once you get it all. So that's the thing. So to work on drawing, work on seeing the symmetry. So then so basically what I just said is all right here. Now let's look at those character tables. I've got a whole bunch here. If I could get y'all to help me pass these out. Pass these around. If you have some from lab, these are the same, so it gets you half of them. I'm just going to pile a bunch of them here. And it's mainly just to show you all the different character tables. You see, in the character tables, you have all the symmetry elements. Like to get to an octahedral compound in the flow chart, you have to identify that it's not linear, that it has multiple C3 axes. Let's see. Well, okay, there's 1, 2, 3, 4, 5. There's 5 questions, okay? So 5 questions to get to octahedral, but look at how many symmetry elements octahedral has. It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different columns of symmetry elements, okay? So you're not learning about all of the symmetry elements and just getting through the flow chart. But once you get the character table for octahedral, you can come here and you can see, yes, it has an inversion center. Yes, it has C2s and C4s and C3s. It has some S4s and some S6s. So it's got all kinds of crazy symmetry. Lots of reflection planes too. But still, all of those Millikan notations, these different designations here, are basically how the different wave functions are affected by these symmetry operations. And the only even row in this is the top row. So it doesn't matter how big the character table is, the top row symmetry is the only one that is going to give you a non-zero integral. So when you have those three, you have 2 wave functions and light being multiplied by each other. The product of all 3 of those things has to contain the top row. or the integral is 0. So this is the character table. We have this piece in blue is the actual character table. We have the Schoenflies notation for the point group up in the corner, so we know which character table we're working with. These are Millikan notations. So that's a new word. We had the Schoenflies notation for the point group, Millikan notation for, I would say, the wave function symmetry or the motion symmetry, the motions of particular things. Like this little R's here, that would be like rotation around the x-axis. So if I took the rotation around x and I did a C2 on it around the z-axis, it would look like it's rotating the opposite way. So it would be a -1 under that symmetry element. So these are the ways those different behaviors of the molecule, whether it's a wave function or a translation or a rotation, behave under each of these symmetries. And that's why it would be called B2 and not A2 or A1, because it has a different symmetry than those others. And so these things in the middle are the characters. And these are Cartesian and rotational basis functions. This means things in the molecule that they're kind of like helpful results. You don't have to reinvent the wheel. They're given to you right here. So the x-axis in this molecule is B1. So light polarized along the x-axis will have the symmetry of B1. Light polarized along the z-axis will be A1. So you can look up light in this table by picking X, Y, or Z. Y polarized light would be right here, and that would be B2. If this is water, heads oxygen, hands are hydrogens, the z-axis is up here, and it's a symmetric stretch like this. The dipole moment is oscillating up and down on the z-axis. When I stretch those hydrogens out, the positive part of the molecule gets further away from the negative part of the molecule. So that dipole moment is stretching and compressing with this vibration. And that's along the z-axis. So that motion has the symmetry of the z-axis and is A1. So we would call that motion an A1 motion. So this is how we build that transition dipole moment integral to determine if Z polarized light could interact with the symmetric stretch. And it can, because it would be A1, A1, A1. So y'all did that in your homework. That was for water. The asymmetric stretch was this one. So now all the positives are moving this way, and the negative is just barely moving that way to keep the center of mass from moving. So it's a great dance move is like this. Okay, so that's the asymmetric stretch, and it's moving left and right. Well, Z, X, Y, that's Y symmetry. It's moving along the y-axis. The dipole's doing this, and it can interact with y-polarized light. So that's B2. So for the asymmetric stretch, it was B2 times B2 times A1 would give you the non-zero integral. So we've done that a little bit. So what do y'all want to practice on? Do you want to practice on that, or do you want to practice on drawing molecules using the flowchart? Okay, let's do for all. Okay, let's pick there was a mistake on the quiz. That second question, I think it was number 10, said ammonia when it should have said water. Okay, so I went in and I changed the PDF and I changed the test so that question was water. Did y'all see that? Okay, maybe the ones doing this Saturday, yeah. So check that. I don't know how ammonia got in there. Yeah, so all right, so let's go back here. I'm going to zoom back and find the blank page. Yes? Okay, very good. I don't know if I can draw well enough to do that one. That's a challenge. But let's try it. Okay, so it's typical to draw the chair conformation like this. Okay. I tell you to be good artist, and then I have a tough time with it. So does that look like a chair conformation? Little chaise lounge? I think it should be the chaise lounge conformation chair. But it'll help if we put the axial hydrogens on here. So there's a hydrogen that comes up like that, and then there's a hydrogen that goes out like that. Okay. And so these axial hydrogens point up like this and point down. The reason I say it's useful to do those is because they are along the z-axis. And so that's telling you where your z-axis is. So it really should be drawn. I mean, if we were to, you can draw it this way, but your symmetry axis is right here. This is your C3 axis. That's the highest order axis that we have, and so that's the z-axis. So it's a little weird when you draw your coordinate system. Z has to be tilted like that because you drew the molecule tilted. And then this is like we draw our little Cartesian system, and so this is x and this is y. So x is coming out of the paper and y is in the paper, but it's just tilted a little bit. So if you wanted to try to draw it to where z is straight up, you'd have to draw it like this. Okay, that's way better. So then now my z-axis is straight up. I'm just going to draw it straight up above it like this. Okay, great. Does that look better? Yeah. Now, I mean, of course, we could draw all the hydrogens and it gets really confusing, but you know, this is probably good enough because that's what an organic chemist would draw, and then we know the hydrogens are omitted. There's no double bonds, so we have CH2s all the way around. It might be a little difficult to see, but anyway, that's what it is. Now, the x-axis is a C2 axis. So think about that. So this is, if I rotate this, you know, 180 degrees, look, that carbon becomes this carbon, and these two carbons change place. Okay. And so this has a C2 axis coming right out of the paper. Yeah. And it has threefold symmetry. So if I rotate the molecule 1/3 of a turn, it's going to look the same. There's another C2 axis. And if I rotate it 1/3 of a turn, there's another C2 axis. So there's three C2s perpendicular to the C3. That's one of my important questions on the flow chart. Okay, so let's go through the flow chart. Is it linear? No. So I'll just write down here. This molecule, linear? No. And then the next one is, does it contain multiple C3 axes? No. It's got one C3 axis. Okay, so it's not a supersymmetric group like a octahedral or tetrahedral or anything. Does it contain a proper rotation axis? Yes, it contains a C3. We determined this up here. Okay. The z-axis is a C3. So Cn, yes. So then we pick a C3. We pick the N, the one with the biggest N. So we have a C3, and so what we want is three perpendicular. No, let's see, three C2s. Let's write it that way. Three C2 perpendicular to C3 question mark, and we would say yes. That's the trickiest one. It's so hard for me to draw. Yeah. Yeah, so this is coming because it's coming out of the paper like this. It's coming out like that. So that's the rotation axis. It breaks both of those bonds. Yeah. So is this the chair thing you see like that? Okay. If I could flip this way. Rotating that way. That's why I drew the arrows. But it's a C2, it goes 180 degrees. So it flips 180 degrees. That's what the arrows are showing. The C2 is 1/2 of a full turn. The C3 is a 120. So it's the three, like think of those three top carbons. They trade places. Um, yeah, so these are the three top carbons, and you do a C3 and they just They trade places. And so then the three top carbons trade places and the three bottom carbons trade places. I know you're having a hard time because you think a chair, the flat butt of the chair has to be flat, right? But it's tilted now. And we're not rotating it around the butt of the chair. We're in the chair. And we're not rotating it this way. Okay. It's this like this, and we're rotating it this. Yeah. 1/3 of a turn. It's all tilted and the axis goes through the center of the butt of the chair at an angle. And you have carbon, carbon, carbon. And so those carbons are trading places. There we go. Yeah, yeah. So that's a fun one. It's like way better than Sudoku. I mean, you sit here, you're scratching your head, and Sudoku's so stupid. It's just it's 91 or 81. I can't 81 if then statements. That's it. If there's a 4, it's not a 4. If there's a 1, it's not a 1. I mean, that's just brainless. But this is great. This is fantastic. Trying to see the three carbons that change place. And so then there's once you do the rotation, then you've got 2 new carbons in the front, 2 new carbons in the back, and you've got a new C2. So you rotate it a third and look, yeah, there's another C2. Rotate it a third, oh, there's another C2. So I have 3 C2s perpendicular to the C3. So you can cheat that way. Instead of trying to visualize the C2 that comes off at some other angle, you can just say, okay, I've got a C3. I rotated a third of a turn. Is there another C2? Yes. Yeah. So that's good. And if you find one of those C2s, you're going to find the others. Yeah. So if there's not any C2s at all, then you just answer no to that one. Yeah. It's not like you have a C3 and you find only one C2 or 2 C2s. If you find a C2 perpendicular to the C3, you're going to have all 3 of them. Yeah. Yeah. That's right. Yes. Maybe there's an exception, but it'd be a weird molecule. I haven't seen that. So, all the ones I give you, you're going to have that. So okay, so yes to that question. Then we get over into the D groups. Does it have a horizontal reflection plane? Okay, so I'm just going to use it. Sigma H, question mark. So that would be the XY plane. That would be this. I don't want to trash my molecule, but that would be this plane right here. So that's pretty good. Kind of like a carpet that goes through the middle of it. And the top does not look like the bottom, right? The carbons don't have anything to reflect into. And so we would say no. And then does it contain N dihedral reflection planes? Oh, we're going to have a hard time seeing this one too, aren't we? Where? Okay. Okay. The plane of the paper. That's one of the reflection planes. You see that? So the front of the molecule and the back of the molecule. So our chair here, it's tilted like this, but the front and the back are the same. So the paper is one of the reflection planes. And then you rotate it a third, you got another one. You rotate it a third, you got another one. So you have 3 reflection planes that contain the principal symmetry axis. So yes, so there's sigma, so it would be 3 sigma Ds. Yes. Because that's the plane of the paper. So I'm going to draw this one intersecting that one. So this little guy right here is the sigma H. And I'll say no sigma H so that you know I'm not pointing out a sigma H. And then the plane of the paper is the sigma D. And there's always a question every year, I can't tell the difference between a sigma D and a sigma V. You'll never, ever have to determine which is which, okay? So they're essentially the same. I really wish they didn't do a D and a V designation because there's really no difference. Okay, the sigma D's and V's are different than the sigma H. The sigma H is always perpendicular to the symmetry axis. So if you have your principal symmetry axis, the sigma H cuts right through the middle of it and is flat with the axis going up. But the sigma D's and V's contain that axis. You see the difference? So the sigma H is horizontal if the axis is up, and the D's and V's are vertical. V stands for vertical. So D stands for dihedral. And that makes sense in benzene, and that's really the only molecule that I come across where the D's and V's are easily identifiable from each other. But they're both vertical planes of symmetry. So the one in the paper is vertical with respect to this molecule. The one that it doesn't have is horizontal. And we say, yep, that doesn't exist. So we've gotten down here. So then we've answered the question, and it's DND. So DND, we have threefold symmetry. So it'd be D3D. So that's our. So there you go, cyclohexane. We did it. Okay. Then we would say, let's now do some spectroscopy with it. So we've got these little CH2s. So a CH2 on this side. CH2 on this side. And I want to show this asymmetric stretch. So this hydrogen stretches out while this one compresses. Okay, that's on this ends of this molecule. The hydrogens are doing. Let's just do it like this. My arm's too long. Anyway, you see what's going on. The hydrogen's going that way while this one compresses, and then like that. So on this big molecule, that's one of the stretches that could happen. And so the hydrogens are positively charged, the molecule is negative, or they wouldn't be attracted to it. And so, which direction is that positive charge going in terms of our Cartesian coordinate system? It's a complicated molecule, but just look at the coordinate system. You see where the arrows are on our hydrogens? What axis do those arrows correspond to? And so remember, we're using this one here. We're not using this one. So I'm just going to scratch all that. So looking at this one, which of these axes do these arrows closely resemble? Y, exactly. So this motion here, so then we have a particular motion. This is Y symmetry. We go to our D3D character table. I hope it's on here. Yeah, hot dang. Down here in the bottom corner on page 2, D3D. D3D. That says this symmetry, you see over on the right, it says X bracket Y. And that's telling us, if we want something with Y symmetry, that's the row we're looking for. It's EU symmetry. So Y symmetry is equal to EU symmetry. And so that would be the symmetry of that motion. And then if we were going to do some sort of light experiment for this, let's say the ground state of this molecule is AG, and then we have EU symmetry for this vibration, and we want to know if these wave functions, after they interact with light, are compatible and have a non-zero integral, so light goes in the middle. And what we need to do is we need to somehow cancel out that E and somehow cancel out that U symmetry to get it to contain some AG. And we could have Y polarized light. If this motion is going along the Y-axis, it makes sense that light going along the Y-axis would also interact with it. And so let's use Y polarized light and put EU there. So this is just showing you, we're going to practice this more after the test. This is just one example, but this is where we're going with the material. Once we have all three of these pieces in our transition dipole moment integral, we can determine if it's allowed or forbidden by symmetry. So then we go to the last page. These are the direct product tables. Over here, that last page up at the top, you see direct product tables. And we find the one that contains the D3D, upper right-hand side, up here. Upper right-hand side, D3D. Oh, what do y'all have? You have it? Yeah, there you go. That one. Yeah. Okay, so this one. So we can take the E times A1. This should be A1G. Sorry. E times A1 is going to be E. And then G times U. If you notice over here, there's general rules. This says G and U rules. So G is even, U is odd. So what do we have when even times odd? We have odd. So G times U is U. And then we bring this EU down. We redraw our little integral brackets, and then we go back to the direct product table, and E times E is A1 plus A2 plus E. And then U times U is G. So we have G on all of these. And then we close our integral. We have a square. Now notice these are now plus signs. So is that something that we've seen before? Yes. When you looked at the integrals and so on, sometimes when you do an integral, maybe you do a trig substitution, now you have things plus each other. Okay, so you essentially have three integrals, but this is top row in that character table. So this piece of this long integral is going to be non-zero. This piece will be zero because it's not the top row, and this piece will be zero because it's not the top row. But this transition dipole moment integral contains one element that is top row. So we can confidently say this is not equal to zero and is allowed by symmetry. So I just wanted to take this complicated molecule like cyclohexane, go to the character table, like pick a vibration or something in the molecule, and this picking the vibration part is not on this exam. But I just wanted to give you this is where we're going with this. We have a little bit more time to work on another problem that you're curious about. Let's do what do you call it? A speed run, okay? Give me an example of a C2V molecule. Ah, good. H2O. Okay, what about C3V? Ammonia, NH3. Or what'd you say, chloroform? Yeah, that's good too. Give me a D3D. We just did that. It's kind of hard to see though. Ethane. Ethane like this. So H, C, wedge dash. Takes me longer to draw it than anything else. See, and look where this next plane. So see, this is the straight line on that side, the straight line on this side between the wedges and dashes. That's the D3D one. Okay. So when you get to ferrocene, you have 5 things on top. But if they're staggered, it's D5D. If they're eclipsed, so D3H. C, H, C, H. Look how the wedges and dashes are on the same side. And the straight line is on the same side. That's D3H because there's a horizontal plane of symmetry. That's that question on the flow chart that splits the two. Do y'all remember Newman projections? All right. This is the Newman projection. for D3D. Okay, so let me just draw a box around this one. And then this one, yeah. So we have H's on top of each other. See, organic chemists do have some useful things after all. Okay, good. Does that help? Yeah. Notice how close my wedges and dashes are. Don't do this business. I'm telling you, don't do it like this. See, that is bad because this is too far apart. Okay, so because those are supposed to, from your perspective, be right in front of each other. So you can see the reflection plane over here. This is a reflection plane. I can easily see that. Over here, can't see it because they're not on top of each other. So I'm not telling you to draw these molecules accurately because I'm picky. I'm saying it helps you the more accurate the drawing. Okay, I think you're going to do great. Study the homeworks. Okay. What's that? Yeah, I do. Yes.